In 7.2, we're going to continue our study of solving systems of equations. This section, for some reason, just limits our study to linear systems. Just a reminder, we came off from 7.1 and we would be given a system of equations such as a quadratic equation and a linear equation, and we used substitution or graphing to find those intersection points. In this section, for some reason, again, they just limited it to linear systems. Okay, but what our objectives are in this section are to use a new method of solving a system, and that's the elimination method. And we'll continue to visualize the solutions that we find. What does it mean when we find the x, y values that we do? So, quick review, as I said, we've gone through graphing and the substitution method in order to find these solutions of systems so far. This was from your 7.1. So before we head into what elimination is all about, one quick review from the past is, from the way past, is what are multiples? A multiple is just a multiplier of a number. So for example, multiples of 2 would be 2, 4, 6, 8, and so on, because 2, you could take 2 times 1 and get this. 2 times 2 and get this, 4, 2 times 3. So all of these numbers in this set that I've started to list out, all of those numbers you can multiply something, some integer by 2, and you would get this set. Alright, least common multiples of numbers, or LCM. Let's take a look at something like 12 and 18. So we want the smallest value that's shared by everything. So if I start to list multiples of 12, of course there's 12, 24, 36, dot, dot, dot. Okay, I'm going to stop because I do happen to know if I generated the list of multiples of 18, I would get this 36. Okay, keep in mind if we went further down the line, 48, 60, 72, if we went farther down the line, we would eventually get further numbers in common, but we wanted the least common multiple. Okay, so LCM. Oh, and just really quick review. If you have like an ACT or something, another way to find an LCM is to do your factor tree. So you could break down 12 into 3 times 4 and 2 times 2, and then 18 we could break into 9 times 2 and 3 times 3. And what we do is we would circle and cross out a pair that's shared, and then I'm going to circle this 2 because I could also cross out that's shared. These are extra guys, so I'm going to box any kind of extras that I have, and then you can just multiply all those numbers. So if you take 3 times 2 times 2, you're going to get 12 times 3, we're going to get that 36. Okay, so you circle some common and shared factors, and then box any of those leftovers, and then multiply them all up. So in this section, like I said, going back to our goal, we're trying to do that elimination method, and the biggest goal in that elimination method is to establish opposite coefficient LCMs within a column. Okay, that is our big major goal, so I'll put a heart next to that. So that brings us now to our method 3, which is going to be solving a system with elimination, and I am going to be doing number 41 from your homework right here. So here are the steps. You're going to want to write those down, but otherwise I'm just going to work through this with those steps. So the very first step is to put the equation so the variable terms are on one side. I can see up here the top equation is just fine, but my bottom one isn't. So I'm going to subtract off x here, subtract off x here, so that's gone. So this now becomes, we have negative 2x plus 8y equals 19. And on the bottom here I have y minus x equals, and then we had negative 3 left over. Alright, step 2, we're going to line up columns to be like variables. So you can see here I don't have like variables in this column or this, so I really need to make a switch. Since subtraction is not commutative, I am going to change that to addition and negate this sign. Now addition is commutative, so I'm going to have negative 2x plus 8y equals 19, and then on the bottom I have negative x plus y when I switch those around equals negative 3. Alright, so here is where we're headed. We said our biggest goal is to find or establish opposite coefficients in one of our columns. So again, our coefficients here, we have 1 and 1. So 1s are very easy to work with, of course, because we can multiply 1 by anything to get what we're hoping for. So I'm just going to focus on this first column here. So multiply each equation fully to establish a column of LCM coefficients. That's our goal. So I'm going to look at 1 and 2. What's a least common multiple of 1 and 2? Well, 2, of course. And so I'm going to take this whole equation and fully multiply it by -2, because I do want to multiply it by a negative so that it becomes a positive, and that way we have an opposite of this -2. So when I decided to multiply this -1 by -2 to get that opposite coefficient, I am going to have to multiply everything by -2 in order to keep this equation balanced. So the top I left alone, so I guess this is kind of deceiving because I said each equation. You only do it until you meet your goal, and this first equation I did not have to multiply anything by. So there's the top. The bottom then is going to become -2 times -1x. That gets me my 2x, exactly what I wanted. Plus, we have 1y times -2, so I do have a -2y here, equals, and then -2 times -3, I have a 6 here. Alright, so that completes steps 2 and 3. Now we're going to add both equations column by column, and we're going to be aware that one of these are going to cancel out. This column is going to cancel out exactly like we designed it. And when we add these together, what we're going to get is 6y and then equals 25. We have brought this system down into now just a one variable equation, and we can certainly solve one variable equations within this equation here. So we have divide both sides by 6, and then y, it's a little bit ugly, but y equals 25 over 6. Alright, so we're going to, if you wanted to, you could simplify this. We are going to get 4 and 1/6. Okay, but otherwise we're going to now solve the one variable. Oh, sorry, we just did that. We did this, and now that we got this y value, we can go back to any of these equations up here or these equations, because I mean these equations are the same as these, just maybe manipulated a bit. But we're going to solve for our variable x. So I'm going to just use this equation right here, and I'm going to plug in 25/6. So we have 25/6 plus -x equals -3. So I am going to subtract off 25/6. So minus 25/6. And then that's gone. We have -1x equals, so gosh, we have -18 over 6 because I need a common denominator for -3, minus 25/6. So we're going to get -43 over 6. So -43 over 6. But then when we divide by -1, this is going to become positive, this is going to become positive. So x equals 43/6, which is approximately, or which is 7 and 1/6. So our final answer is 7 and 1/6, comma, 4 and 1/6. There we have it. What I do want to show you then, we just came up with 7 and 1/6, comma 4 and 1/6. So if you do look up here, had we graphed it, because I solved for the y's, got them in y equals mx plus b form, and there is our point, and you can see, yeah, that's approximately a little bit past our 7 and a little bit past our 4. Okay. One thing that can still happen are those 3 possible outcomes when solving these linear systems, which is exactly what we're doing. It's the same chart that I presented in the other PowerPoint on 7.1. Just note here in this last column that substitution and elimination now is all together. So when we have one solution, we get nice x equals this, y equals this. The infinite, we still get that true weird statement, and then for our no solutions, we get an untrue weird statement. Okay, so elimination, the same type of thing is going to happen that we had in substitution. There's your practice.